that in itself is all very nice, but these weights need to match the original requirements. So if when we sum up all of the weights of these systems, we no longer can put two people in the vehicle, then we don't have a closed loop. So we need to revisit this. Weight is exceptionally critical, as I'm sure you can imagine, for an aerospace company. So it's probably quite a basic view of how we're developing our system. But essentially, any engineering problem can be addressed by taking this systems engineering approach, and we don't do anything different in that respect. I'm just going to show you a quick clip of the outcome of our development on V8X2. You may have seen it before. It's on our website and YouTube, etc. But I'll show it because it's quite impressive. As I'm sure you can imagine, the first time that took off, it was quite a nerve-wracking few moments. But it completed its successful flight test campaign, quite notably before the City Airbus, although City Airbus, I think, went on to achieve slightly more than we did with our program. We decided that V8X2 had done enough and given us enough information to move on to what we're now calling V8X4. And I think the main event for the company for the next 3 years, probably. So to take a bit more of a look at V8X4, we are targeting to fly 100 miles at 150 miles an hour. Now we should achieve slightly more than that, so maybe 120 miles at a slower speed or a shorter distance at a higher speed, around 200 miles an hour. But that's kind of in about what we're targeting there. All electric, as the name suggests, eVTOL. And we're targeting missions like shuttling from city centres to airports. This is a pretty standard target for us, where to travel this by car you're looking at an hour and a half probably, and here we can do that same journey in 20 minutes. 1 pilot, 4 passengers, and that's passengers with luggage. Really crucially, low noise. So just staying on London. London is limited on the number of helicopters that can fly from Battersea, actually, in the centre, because of noise. That is the limiting factor. So we reduce noise, we're quieter than a helicopter, we can get more flights. And also, quite critically, more affordable. We want to bring this type of transport to the masses. That means we need to be more affordable. We're targeting to be cheaper than a black cab, I think around $5. So what's that, £3 a mile or something like this. That's quite a step change for this type of travel. I'm just going to focus a bit on one of the real noticeable differences with this vehicle compared to Seraph. Obviously, we have wings now rather than just a multi-copter, but we've also got articulated rotors or propellers or prop rotors, as we are now coining the phrase. So these have two jobs: propel us forward and to maintain us in vertical flight. We're doing this through an articulated joint or tilt mechanism. So we have to move the electric motor through, it's actually about 100 degrees. So we want to go past the vertical to give us some elements of yaw control. And to do that, we've got to create quite I would say complex. I'm sure there's more complex joints out there, but it's complex through its need to be extremely robust. Any failure for this mechanism could be quite problematic. So we now add into our development this tilt mechanism. And just going back to our previous systems engineering view, this tilt mechanism is going to have an effect on how we're developing the motor, the inverter, and the associated cooling system. As we no longer can fit everything in one space, we have to spread out the design of those systems across that tilt mechanism. But essentially the process is the same.